In the last episode, I described Claude Bernard's idea of homeostasis as weird. Let me clarify that. Here are those quotes from that last episode, which outline Bernard's concept of homeostasis. In our time, Bernard's thinking has been boiled down to that one quote. The other quotes contain some more subtle messages, though. When Bernard writes of the constancy of the internal environment being the condition for a free and independent life, he clearly means that the constancy is antecedent to the free and independent life. In the next quote, he implies an opposite chain of causation, that is, mechanism that makes the constancy possible. But then he goes on to speak of characteristics of the organism, including a supposed perfection, and even the capability of wisdom. What should we make of this? Well, it actually all fits together, and here's how. Here's an internal environment. Let's stipulate it has constancy of some sort. Let's say, just for argument's sake, that it's constancy of temperature. Bernard, being the physiologist, would naturally be interested in the internal processes that are going on in there. The question is, which gives rise to which? Is it the processes that give rise to the constancy? Well, that's a natural way to think about it, but Bernard's famous aphorism seems to belie this. According to him, it's the constancy that allows the free and independent life. And this would mean that the chain of causation is actually the other way around, namely that it's the constancy that gives rise to the processes. Now, that's the weird proposition. Yet it follows from Bernard's logic that the constancy is the antecedent, life's fundamental property. Now, here's the thing about fundamentals. Everything streams from them. Fundamentals are just there. They're not derived from anything. They're fundamental. If Bernard's constancy of the internal environment is the fundamental property of homeostasis, this means it's the processes that must stream from the constancy. Bernard's own concept of homeostasis derived largely from someone we have encountered before, Théophile Bourdieu of Montpellier University. We remember him as the originator of the many little lives doctrine. Let's remind ourselves also that Bourdieu was inspired to this idea by the coordinated behavior of bees in colonies. To him, the assemblage of bees in a colony behaved in many ways like an organism. Vital fluids could not explain the swarm's organism-like properties, Bourdieu argued, because swarms were not contained within organisms. Swarms were many organisms, many little lives. This was the origin of process vitalism and the demise of essential vitalism. What governed the emergence of organism-like behavior from the many little lives were processes, communication and mutual accommodation between all of the many little lives. No matter whether the many little lives were contained within an organism or with assemblages of organisms, it was the process of negotiation and mutual accommodation that forged the many little lives into an organism. Bernard's inspiration for homeostasis derived directly from this way of thinking. To Bernard's mind, an organism, like say a fish, incorporates within its body an internal environment. At the same time, the fish lives in an external environment, water in this case. To coordinate their activities, the fish's various many little lives have to be able to communicate with one another, and the internal environment is where the negotiation takes place. Bernard, being a physiologist, was focused on clarifying the processes of communication, negotiation, and mutual accommodation among the fish's many little lives. And obviously, he was very successful at doing that. But what really interested him was the adaptability. Adaptability meant that the fish could live in a variety of external environments and still maintain its integrity as an organism. The internal environment had to be constant for that to happen. Even though Bernard was not himself an evolutionist, this idea has obvious evolutionary implications. For example, what if the fish moved onto land? Now the external environment is very different. It's no longer water, but air. But the fish still has an internal environment to maintain. The same processes have to go on inside the body of our terrestrial fish, with communications between all the parts still mediated through its internal environment. If the constancy of that environment falls apart, so too does our erstwhile terrestrial fish. The fish therefore has a certain independence from its external environment. The constancy is the antecedent to this independence. Following his death, Claude Bernard's more philosophical ideas languished. It's easy to see why. The scientific climate of the early 20th century was not congenial for vitalism-tinged ideas, like Bernard's homeostasis. In the 1930s, however, homeostasis enjoyed a revival, thanks to this man, Norbert Wiener, an engineer at MIT. Wiener was the father of what we now call cybernetics. Wiener himself defined cybernetics as the scientific study of control and communication in the animal and the machine. To Wiener, animals were the epitome of the self-regulating machine, self-directed, persistent, and adaptable, and Wiener wanted to build self-regulating machines. Naturally, Bernard's thinking, especially about homeostasis, resonated strongly with Wiener. To build self-regulating machines, Wiener had to reconcile the essentially vitalist idea of homeostasis with engineered process. And the result was the emergence of something I call the clockwork homeostasis. I'll come back to what I mean by this in the next episode. Wiener laid the foundations for cybernetics prior to and into World War II. His work then was directed to the development of self-steering anti-aircraft weapons and projectiles like torpedoes. He drew obvious inspiration from the living world. A cheetah, for example, could automatically steer its own way toward its prey. And why couldn't a torpedo do the same thing? Perhaps the self-steering ability of a cheetah could be imitated in a torpedo. Wiener's solution boiled down to defining cybernetic machines, which he defined as how machines manage information and use that information to do guided work. From there, Wiener went on to lay down the theory of cybernetic machines, as Newton did for matter and motion. He was on that scale of intellect. Cheetahs and torpedoes are both complex cybernetic machines. So let's turn to a much simpler cybernetic machines, a regulator of house temperature. The thermostat mounted on your wall is part of a cybernetic machine called a negative feedback controller. The rest of the cybernetic machine manages heat flow across the walls. Most modern homes have two machines that do this: an air conditioner, which pumps heat out, and a heater of some sort, which pumps heat in. The cybernetic machine works this way. The thermostat compares two bits of information: the set point, which is the temperature we desire, shown here as the red needle. The set point is what we manage by turning the thermostat up or down. The thermostat also senses the actual house temperature, which we'll call the sensed temperature. This is indicated here as the blue needle. We can see why this is called a negative feedback controller by following the typical temperature of a house regulated by the thermostat. Here's the set point temperature, indicated with a red dashed line. The sense temperature will vary up and down. When the sense temperature rises above the set temperature, the AC will be switched on, pumping heat out of the house, and the house temperature will then fall. When the house temperature drops below the set temperature, the air conditioner will be switched off and the heater switched on, and the house temperature will then rise. This will continue indefinitely, keeping the house temperature steady within a narrow band, no matter what's happening to the climate on the outside. This machine is called a negative feedback controller because the house's sensed temperature feeds back onto the set temperature to negate whatever perturbation there is from the set temperature. If the perturbation is too high, that is too warm, the AC is switched on. If the perturbation is too low, that is, too cool, the heater is switched on. If this is looking familiar, it should. This is an example of an adaptive boundary, which we've explored in some detail in previous episodes. Cybernetics was essentially an engineering philosophy. It drew inspiration from biology, but it did not presume to be biology. However, cybernetics proved to be such an intriguing idea that biologists soon took it up as a way of explaining how animals worked. The first example of what we might call biological cybernetics was regulation of body temperature. Here's a bit more of a technical description of a negative feedback controller. You have a set temperature and a sensor of the actual temperature of the system, and these feed into a device called a comparator. The comparator compares the set temperature versus the sensed temperature. If the sensed temperature is too high, the cybernetic machine activates what we will call heat loss effectors, like the heater or air conditioner of a house. This feeds back onto the system temperature, reducing it. Conversely, if the sensed temperature is too cool, this activates so-called heat gain effectors, which also feed back onto the system temperature, elevating it. What biologists did was to translate this into a metaphor for regulation of the system properties of animals, like this mouse. There had to be a comparator in there somewhere, which compared a sensed body temperature versus some set temperature. If the body was too warm, various mechanisms were activated for facilitating heat loss. And these could include a depression of metabolic heat production, reducing the fur thickness, and so forth. All would act to reduce body temperature. Similarly, if body temperature was too cool, this would activate mechanisms for conserving heat within the body. Thus, homeostasis of temperature in an animal has been reduced to the operation of a cybernetic machine. In fact, understanding body temperature regulation of a mouse doesn't even require the mouse. It's simply a machine, a clockwork, if you will. We'll be returning to a critique of the clockwork homeostasis in the episode to follow. In recent years, the concept of homeostasis has been undergoing yet another transformation. This one is related to the thermodynamics of life, which we discussed briefly in a previous episode. We return to it now. Here's the question. If we start with a disorganized puddle of stuff, how do we get a living thing out of it? The old vitalist idea asserted that some ineffable vital force would impart life to this otherwise inanimate matter. This was Aristotle's concept of anima, the animating principle of life. We no longer believe in that, of course, but we can now reframe the question by approaching life and homeostasis as a special case of the second law of thermodynamics. To get life out of inanimate matter, we have to use free energy to do work to mold the otherwise disorderly stuff into an orderly living organism. Let's put this in terms of modern thermodynamics, and entropy is a crucial word to know here. It simply means disorderliness. The second law of thermodynamics is the physical theory of order and disorder. We don't need to go into that theory too deeply. For our purposes, we can simply say that the mass of undifferentiated stuff has high entropy or high disorderliness. The living organism is that disorderly matter organized into a highly specified orderliness with low entropy. Now, there's something important to understand about low entropy systems. They're disequilibrium states, and this makes them inherently unstable. The second law of thermodynamics says this explicitly, that disequilibrium states will always degrade to equilibrium states, that is, to states of high entropy. Our living organism is a highly specified disequilibrium state. This means that the organism will continually degrade back to equilibrium, that is, to the state of unspecified disorderliness in that puddle of stuff. We don't see this degradation in a living organism, but it's there. It becomes visible when the work being done to sustain the organism goes away. Death, in a word, Here, the degradation now emerges. It's only because we continually do work on the disordered stuff that we see the organism persisting in time. The organism persists because it's doing order-producing work at a rate that offsets the rate of degradation and collapse to disorder. And this is a new way of looking at homeostasis. Let's express it in terms of the standing wave concept we described in an earlier episode. We can describe the standing wave as a relationship between orderliness and what we might call quality of energy. Free energy is at the left, which is energy that is capable of doing work. To the right is energy as heat, where energy goes when the system comes to equilibrium. The second law asserts that this axis has only one direction. Free energy always degrades to heat. High-quality energy inevitably decays to low-quality energy. Along the way, the free energy does work, increasing the orderliness in the system, culminating in the frothy wave of the crest, and the organism rides that frothy wave. Following that, this disequilibrium state degrades spontaneously to disorder or high entropy. This is an ongoing process. The standing wave, remember, appears stable even though it's continuously changing. In the case of our living system, matter is taken from its disorderly state and formed into the highly specified orderliness of the organism. At the same time, the material in the organism is continually recycling to disorder. This is a continuous process, with matter cycling between states of orderliness and disorderliness. Homeostasis is thereby redefined. Homeostasis is the sustaining the organism's state of specified orderliness in the face of its continual degradation. Persistence in time, in a word. Homeostasis is the persistence of a disequilibrium state. We'll be coming back to the thermodynamic dimension of homeostasis in subsequent episodes, because it has relevance to how we think about evolution and Darwinism. But let's wrap up this episode with an interesting historical digression involving one of the more colorful characters of 19th century biology, Edward Drinker Cope. Cope was a vertebrate paleontologist. He's best remembered today for his pioneering work opening up the immensely rich fossil beds of the American Midwest. He was quite a flamboyant character, obstreperous, and difficult to get along with. The part of his public persona that survives to this day centers around the intense rivalry between him and Othniel Charles Marsh of the Peabody Museum at Yale University. These two men were in intense competition to dig up and bring new fossils to the world. Their competition including sabotaging each other's digs, so it's no surprise that this competition came to be known as the Bone Wars. Several books have been written about this remarkable episode in the history of American science. Here's one that I particularly enjoyed. Cope is the man on the top of the cover, and Marsh is at the bottom. Cope's scientific impact in paleontology and vertebrate zoology was immense. The official journal of the American Society of Ichthyologists and Herpetologists is named after him. What's been largely forgotten about him today is his extensive writings on evolution, which were a trenchant critique of the Darwinian idea. His two principal books outlining his views on evolution are difficult to find today and are almost never mentioned in the evolutionary literature. In short, his evolutionary work has been shoved down a memory hole, just like Darwin's Lamarckian pangenesis idea has been. Why? Well, it was an inconvenient critique. Shoving Cope down the memory hole has also shadowed Cope's remarkable critique of contemporary evolutionary thought. Specifically, he anticipated, in a strange way, the thermodynamic dimension of evolution I just mentioned. So, what were those ideas? Cope summarized his critique in this way. The Darwinists attempt to explain design and structure through the operation of the survival of the fittest. It's justly argued against this reasoning that it attempts no explanation of the origin of such structures. Let's boil this critique down to what I call Cope's question. Never mind the origin of species, what's the origin of fitness? Cope's own answer to this question reflected another 19th century line of criticism of the Darwinian idea, known as orthogenesis, which we can roughly describe as evolution on a rail. The doctrine of orthogenesis asserted that the history of lineages was mostly explained by large-scale forces that drove them in a particular direction, like a locomotive follows a railroad. In the late 19th century, orthogenesis was all the rage among the critics of Darwinism. The critique boiled down essentially to this. Compared to these large forces, natural selection, if it even worked, was puny and could explain only trivial changes. Cope is important because he was a prominent figure in that fight. Cope's orthogenesis cred, so to speak, is embodied in what has come to be called Cope's law, although it's more appropriate to call it Cope's rule. Cope didn't cook up his rule out of thin air. As Cuvier did, Cope derived it from an extensive body of empirical data from the fossils he had collected. What his measurements unearthed was a prevalent trend for the body size of lineages to increase over time. The classic example of this can be found in the evolutionary lineage of horses, which began as small dog-like creatures in the early Eocene and culminated in the large modern horses. Cope also found this trend of increasing body size in the lineages of many of the fossil dinosaurs that he excavated. Paleontologists still debate the validity of Cope's rule. It's not a universal trend. That's why we call it a rule rather than a law. But we see the trend more commonly than mere chance would predict. It requires an explanation. Cope himself had worked out a whole theory for why, and Cope gave his theory a name, bathmism. The word derives from the Greek, to step. Cope centered his theory on something he called bathmic energy, which he regarded as a universal growth force. In the horse lineage, for example, the tendency to larger and larger body sizes was driven by this bathmic energy, and natural selection, if it worked, could at best account for only small deviations from this overall bathmic energy-driven trend. And this was the basis of Cope's critique of Darwinism. Because Cope's rule has empirical support, you can still find reference to Cope's theory of bathmism, but mostly just as a pretext to denounce the whole doctrine of orthogenesis. If Cope's bathmic energy was all there was to his theory, Cope's ideas would look very much like Lamarck's complexifying force. But Cope took it further than Lamarck did. Out of this came Cope's alternate theory of evolution, which anticipated the thermodynamics of living systems that I just outlined. Cope argued that a living organism was the balance between two forces. One he called anagenesis, basically order-producing work. At the same time, Cope recognized an opposing force which he called katagenesis. This would promote the degradation of the organism into disorderly matter. To Cope, the living organism was basically a balance between anagenesis and katagenesis. Cope's bathmic energy was an anagenic principle, and the persistent organism required a persistent application of bathmic energy. Applying this to evolution, Cope argued that the continuous input of bathmic energy over generations would produce a steady increase of body size in a lineage. That was Cope's explanation for Cope's rule. Okay, let's take a step back. For all of Cope's weird vocabulary and vitalist predilections, this theory closely resembles what I just described as a thermodynamic theory of homeostasis. As far as I'm aware, Cope is the first person to bring an explicitly thermodynamic perspective to an evolutionary question, namely, why is it that a lineage's body size tends to increase over time? More broadly, Cope brought an essentially physical perspective to his critique of Darwinism. The language might be different, and a little antiquated, but the idea of evolution as a balance between order production and order degradation is spot on, in my view.